we present the paper, Classification of Biomedical Journal Images Using Retargeting-Based Data Augmentation and Visually Explainable Attention Priors. The work on this paper was done at the Video Image Modeling and Synthesis Lab at the University of Delaware during the time of submission. Identifying regions of interest in images is vital for solving various computer vision tasks. Convolutional neural networks, CNNs, implicitly detect these regions. Per contra, CNN-compatible retargeting-based data augmentation approaches explicitly detect task-critical regions and enhance their spatial coverage. Retargeting-based data augmentation approaches identify and reduce the noise and variations in the data while training and testing a CNN. These augmentation approaches learn to disambiguate noise from a signal during the forward pass of the network by using an attention mechanism. They reduce the noise by preserving the task-critical regions prior to image subsampling. Consequently, they increase the spatial coverage of the regions essential to a task. However, unlike non-learnable data augmentations, learnable ones have some drawbacks. The obvious drawback is that they perform computationally intensive optimization at inference time and require additional learnable parameters. In addition, the task-critical regions learned by these methods can be inaccurate. However, since these methods do not rely on prior knowledge from a human user about the test distribution, their learning needs to be more precise to generalize across different datasets. Existing works employed attention mechanisms at the start of a network. However, in this work, we hypothesized that attention mechanisms at the start of a network could not faithfully learn the regions of interest. For example, in image classification, research has demonstrated that deeper layers in CNN contain discriminative semantic and spatial information about the classes. Therefore, expecting an attention mechanism to explicitly detect class discriminative regions at the beginning of the network is counterintuitive. Techniques that produce visual explanations for decisions from CNNs can faithfully identify task-critical regions, yet, they are primarily used for interpretability purposes. This paper proposes a data augmentation approach that utilizes outputs from visual explanation techniques as attention priors to retargeting-based data augmentations. Thus, as we will show next, compared to all the existing retargeting-based data augmentation approaches, our approach reasonably conserves the original CNN architecture. In addition, the search space to learn the attention priors for image retargeting is reduced as well. Our data augmentation approach consists of two stages. In stage 1, we train a convolutional neural network on the training set containing low-resolution images. Then, any approach that faithfully outputs a visual explanation for the network's decisions is utilized to obtain task-critical regions on the training and testing images. We consider the visual explanations induced by the network as prior knowledge for stage 2. These priors are employed in stage 2 to perform retargeting-based image augmentations. The second stage is categorized into two subcategories, initialization mode and refinement mode. In the initialization mode, higher resolution images are sent to the retargeting module along with the prior. The retargeting module outputs images at a lower resolution, but the spatial coverage of task-critical regions is increased or at least conserved. In the refinement mode, a refinement module jointly optimizes with a network to relocate task-critical regions in the priors acquired from stage 1. In our approach, since attention is inferred by visual explanation methods near the final convolutional layers of the CNN, the size of attention map is small. As a result of the small attention map, we were able to reduce the spatial complexity of an existing retargeting module from O of n squared to O of n log n squared. For details about this proof, please refer to the section 3 of our paper. The training and evaluation strategy in the refinement mode is similar to the initialization mode besides one aspect. In the refinement mode, we refine the attention priors from stage 1 before propagating them to the retargeting module. The key contribution here is our novel refinement module that softly refines the attention priors to better relocate the task-critical regions in the images. Unlike other methods that used attention mechanisms to learn disassociation between pose and texture, our refinement module only refines the visually explainable decisions by a CNN. Thus, compared to other approaches such as AIM and Saliency Sampler, our approach only requires a few trainable parameters to infer the task-critical regions. Data augmentation approaches have shown that they can improve the performance of neural networks in classifying images of natural scenes. However, the role of data augmentation techniques for biomedical document images has not been completely explored. Designing augmentation approaches that generalize to biomedical document images can improve the performance of biomedical document retrieval systems. Thus, we evaluated our data augmentation approach for categorizing images in the ImageClef 2013, ImageClef 2015, and the ImageClef 2016 datasets. These datasets contain diagnostic or general illustrations from biomedical documents. It is challenging to classify the images in these datasets since most images contain noise in the form of writing. In addition, ImageClef datasets exhibit high intra-class variance and class imbalance. We trained ResNet 50 and DenseNet 121 on the training set of ImageClef 2013, ImageClef 2015, and ImageClef 2016. Then, we evaluated these trained networks on the testing set of these datasets. Classification accuracies from this experiment served as a baseline for comparison with all other experiments. Next, we trained and tested ResNet 50 and DenseNet 121 using different state-of-the-art augmentation approaches on all three datasets. The classification accuracies using data augmentation were generally lower than the baseline results. In particular, no augmentation approach improved the baseline classification accuracy on the ImageClef 2015 dataset. These experiments demonstrated that the task networks learned undesirable biases because of geometric and photometric perturbations to the original data. In the case of non-learnable augmentations, results suggest that randomly removing regions was not conducive to learning. However, as these approaches do not participate in the learning process, it is impossible to constrain them to remove unimportant regions. In the case of learnable augmentations, it is evident that they did not learn and focus on regions that were conducive to the task. To evaluate our data augmentation approach, we used GradCam, GradCam++, and LayerCam in Stage 1 to provide the visually explainable prior. The task network was either ResNet 50 or DenseNet 121. Then, we retrained these models from scratch in Stage 2 using our data augmentation approach. We observed that the initialization mode improved the baseline classification accuracy on all datasets for both models. Naturally, our data augmentation approach also outperformed the 7 state-of-the-art augmentation approaches on all 3 datasets. Our approach in refinement mode also gave higher accuracies than the baseline. Both models obtained higher accuracies on almost all datasets, even after using different visually explainable priors. Our main finding in this work is that accurate attention prior is vital to the performance of the task-specific retargeting-based augmentation techniques. However, further work will be necessary to demonstrate that our approach generalizes to other tasks.